today's lecture is going to basically touch on ensuring that you understand what is this whole deep learning about. Okay, obviously it's a big, huge topic, yeah. But fundamentally speaking, you need to understand the basic idea of it. And if you understand that basic idea, then you can gradually expand further. So, in its most basic form, you will have the deep neural networks, basically. Then you get convolutional neural networks. Then you get autoencoders. Then you got recurrent neural networks. Then it's expanding further into complicated neural networks like convolutional neural networks, such as structures like ResNet, which you know become complicated in terms of its structure. Or further complication comes into graph neural networks, which is a completely different dimension. But all of that, before you leap into them, it's so important that you understand the basic concept of what this AI is all about, yeah? And where did the idea basically initiate from? So I will try to lay the foundation of that for you today, okay? And hopefully, I will try to also, I will keep you on in this bootcamp and I will post more videos for you, but you don't have to attend them or anything. It would be just, material for you to look, okay? So I'll keep you in the loop and you will be getting other stuff from me, but obviously there won't be any live lectures. Anyway, so that's what we are going to be doing. So very quickly, I will cover the idea of deep learning, where it comes from, what is it about. Some of you may have known this, some of you may not, so I thought like quickly go through it. So the whole idea basically initiated from this man, Frank Rosenblatt. He was a psychologist and studying human brain and human activity. He was thinking of somehow constructing an electronic structure that can mimic the functionalities of human brain cells, neurons, basically. And this was basically in 1960s, late 60s, that he was proposing this. Obviously, he did not survive because of a boating accident. And later on in the 80s, the ideas were picked up by these men, especially Jeffrey Hinton and his student Jan LeCun. And the idea of modern deep learning basically started to take life. And this was at the time that computers were becoming more powerful, because ultimately deep learning is nothing but boosted linear algebra. Okay? So let's quickly, I'm going to skip a lot of these and come here. Take a look at this picture, guys. Yeah. I mean, this is a simple classification example. Yeah. So, for example, we usually have, let's say we have a problem of, there is this guy taking certain number of carbohydrates, protein intake, a bodybuilder, different bodybuilders basically, and would they win or lose, a classification. And here what we have is the idea of a perceptron, yeah? So these three dots represent the input data, the green dot represents the actual neuron and what happens in there, okay? And Y represents the output. So today I will be focusing to ensure that you understand what a single neuron or a perceptron is all about. Obviously, real biological neurons are beyond in terms of complexity of what we will be discussing here as a neuron, but technically speaking, that's what we would be sort of talking about this. Let me quickly, if I put neurons, yeah. So that's a neuron, guys. I mean, why is that coming out? So, I mean, this is for example, I said, nice looking image of a neuron, although it's not bringing images for me. Can we look at that? Okay, that's why I hate this Yahoo. I don't know why did he go to Yahoo, Roman Yahoo. Go away, Yahoo. Okay. So if I go to images, I mean, we can think of this. That's a neuron, guys, okay? The idea is that ultimately in, like in biological life form, the idea is that there are certain input are fed into these dendrites, basically, of the neuron head. So some information is passed through here, gets processed there, and then passed along, okay, as you can see. Now, would it be one output, two output, or multi-output? We are not concerned at the moment. Just think of it as one output. But what we are going to be talking about is thinking of this concept and trying to sort of put it in mathematical terms, okay? So that's what we will be doing technically. Let me close this rubbish. Okay. Right, so let's go back to that. And I'm going to bring paint, okay? Yeah, bring paint. So I'm sure all of you are familiar with uh, y equals ax, yeah? Let's just say a. We are all familiar with this, yeah? So you got, you know, some variable y, and then you got this x. There is a relationship between y, yeah, and this x. How is this relationship basically? It's defined by this a at the moment, yeah. So this is a very, very, very basic relationship, between y and x. So if I give you a set of values for x, okay, so if x is let's say 1, 2, 3, 4, 5, okay, and if I tell you that a equals 2, all right, so you can very quickly estimate this and say, okay, if a is equals 2 and the relationship between y and x is y equals ax, then I'm going to be having y as 2, 4, 6, 8, and then 10. Okay? I mean, I hope we are all aware of that. Yeah. So that's the most basic form of basically a formula, right? Now, if we were to think of projecting this into the structure of a neuron, so let's say this is a little neuron, yeah, and it's going to take in one data, okay, and it's going to have an output of one data. Just think about it, yeah. So technically, we are feeding an X to it, yeah. So a little X is fed into this neuron, all right, and it somehow needs to give us the Y out, okay. That's the idea. How does it give the Y out? Well, somewhere in its core, it basically, like something has to happen, and that is A is getting basically multiplied, yeah. So times, well, that's X again. So let's say times A, okay, and that's what you can think of a very simple version of this neuron takes one input in, gives something out. What happens? There is this A that is multiplied in between. Now, what if I was to tell you, let's make this formula a bit more complicated and more exciting. And this time, let me just get rid of all of that. Well, actually, I can keep it so that you don't lose track. What if then I was to tell you that we have a formula y equals ax1 plus bx2 plus cx3. Okay, now this is a bit more exciting. Okay, so this time our y is defined by different parameters involved. Okay, so y is not straightly calculated from x, but rather from x1, x2, and x3 in combination. Okay, And to be able to do that, so if you have a set of values for x's, yeah, x1, x2, x3, so it would be like x1, let's say was 1, 2, 3, okay, and then let's say x2 was, I don't know, point 0.2, 0.6, and 0.8, and let's say x3 was, I don't know, 10, sorry, 10, 11, and I don't know, 12, yeah, just for the sake of it. So to calculate y, you need to know what A is, what B is, and what C is, okay? Just as you needed to know what basically A was here to calculate that. This is the foundation of the idea, you know? So how do we come and define a neuron for this now? So let's create a little neuron, okay? Let's create a little neuron. And this time, if you notice, we are having three inputs basically going to this neuron. Okay, so 1, 2, and 3, and we are going to be having an output. Okay, so we are feeding this neuron now with our x1, okay, x2, and x3. All right, hoping to get y. Okay, so why do we call this a neuron? Simply because, you know, as I mentioned, like the idea was the similarity. Do you see? So it's just a similarity in terms of the structure and the fact that the original guy being a psychologist and looking with brain cells and brain functionality, basically the idea of neurons seems feasible and it's cool. Otherwise, let's call this a perceptron. That's the real name that you should really be calling this. Yeah. So this is a perceptron. Okay. Uh, and if you think about it, okay, so we said that what do we need to do? We need to know A, B, and C that go here. So A and B and the C, okay? So if we know this A and B and C, then we can find Y, okay? But what if, guys, what if A and B and C are not known, yeah? A and B and C are not known. Instead, let's say we know what y is, okay? So y, let's say for this equation, and I'm going to like do y in a different color. For example, let's say y, just so that it's in the same. Okay, so let's say, I don't know, it is 34, 56, 78, it's just number. What if somebody was to come and tell you that, you know what? I know what y is, and I know what the x's were, and I know for a set of x's what y value did I get? Okay? And I want you to find out a and b and c. Okay? Well, technically, that's the whole idea of linear regression. Okay? And that is exactly what, when you say a deep learning model is learning, okay? That's what is exactly happening. So you train your model by having the y values, the x values, yeah? Let's say y is, I don't know, human height, and x1 and x2 and x3 are protein intake, I don't know how much sunshine hits you, and I don't know how much milk you drink or something, yeah? And you want to sort of find the relationship between these factors and human height. Okay, you know the height, you know the output height, you know how much milk and I don't know sunshine and whatever the guy got, but you want to see if you can have a deep learning model that can predict this, yeah? So the idea is if you were to put this into a single perceptron, it's you want to basically find A, B, and C, yeah? So how does the model, how would it automatically get these data and then find these A, B, and C? And that's what I want to focus on you guys understanding today, yeah? The idea of this, yeah? So that's what I really am after. So I hope you have understood what's going on here. Obviously, it's a bit more complicated than this, but provided that you understand this, then we are one step ahead, basically, yeah? So far we discussed this. I mean, like, look at this, x1, x2, and w2, yeah? You know, like that A and B. So shall we start calling, instead of A, we're going to say W1 and W2, because with deep learning, we don't refer to them as A and B and C. We're going to refer to those as weights, yeah? So these, let me go and actually do it there. So instead of saying A and B, yeah, we're going to put a new one, and we're going to say that this is, with deep learning, we don't say A and B and C. We're going to say, just call it weight 1, weight 2, and weight 3, okay, in this example, right? So we're going to refer to these as weights. So it's going to be what? It's going to be what? W1 x1 plus W2 x2, and so on and so forth, yeah? Okay, so having said that, let's take a look at this formula, okay? So we have y, we have the x1, x2, and that's basically, this is a linear regression model, okay? You have seen this before, okay? So it shouldn't shock you. We just went and tried to input those features, like show it in form of neurons, basically, yeah? That's what we were doing. Guys, can you mute your microphone, please? Let me see, who is that? Okay. So the only difference that happens is that with the idea of deep learning, you add a nonlinear function to it. Okay. So when we were looking at this neuron in simple linear regression, that is it. You know. So you multiply these together, add them up, and you get y. Okay. Except that if you come and add a nonlinear function before you feed it out. So in other words, you apply a nonlinear function to these, a nonlinear function such as ReLU, okay? Then you're converting this technique into something that can solve nonlinear problems, okay? But no need to think so much about it at the moment. Let's go and now dive in and understand further about this, yeah? So everything so far was just like a linear operation. We are thinking of two inputs, except that before we get the y, we just, use a nonlinear function and then have an output which is nonlinear, okay? So this we have already seen. We have inputs of 4, 3, 5, okay? Weights of 0.5, 0.3, 0.2, and then we get what? 4 times 0.5 plus 3 times 0.3 and 5 times 0.2. We already showed this, when I was on the paint, yeah? Well, cool, that's just a linear regression, isn't it, yeah? But think of it, guys. How about if we think of it as linear algebra? If you think of this as a vector, 4, 3, 5, and a vector of 0.5, 0.3, 0.2, well, this is really a dot product, isn't it? Yeah? Vector 1, your input vector, and let's call this our weights vector, okay? And then we get a single output. So technically it was like a dot product there, 4 times 0.5 plus 3 times 0.3, 5 times 0.2. Sum it up, that's a dot product. Except that obviously we added that, nonlinear function to it, all right? What sort of nonlinear functions? Well, we can have different types, okay? This is, for example, sigmoid. But when you do it, when you sort of work with these, and when you like watch other material or like you try to expand on this further yourself, you will see that like a function such as ReLU is extensively used, especially in deep layers. And something like sigmoid is used for classification output. Anyway, we don't have time to like cover all that, but there are different types of activation functions that you can use here, okay, which enables your model to solve nonlinear basically problems. I'm gonna skip this. I mean, like these are some of them. ReLU is by far used the most, okay, extremely used in the structure of a deep learning model. But there are many other models as well. You will learn them on your own time, all right? Now, like before, we were looking at a single neuron, right? So here, so we had three inputs, okay? Before, in the other example, we had three inputs. In that, three inputs, a single neuron, and an activation function and an output, okay? So what do we see here now? We are having three inputs as before, but instead of a single perceptron, I got four perceptrons on the front line and another three after that. So all these three inputs are being fed into the first perceptron. Then they are giving an output, and this output is fed to further neurons, your further perceptrons. And that's where the idea of deep learning comes from, because you got these deep layers of neurons, yeah? And or if you call them neural networks, yeah? So you got the networks of these neurons. But I hope you understood what is happening inside each of these single neurons, yeah? That's what I really want, especially for those of you who are new, to sort of understand what's happening under the bonnet here. Because if you understand this, then you can go and watch more, better sort of quality videos and many other stuff on YouTube, and you will then understand what's going on. Okay, but if you don't understand this single bit, and you're going to start try to learn like complicated Python coding for deep learning models, you won't really grasp what's going on. So I hope you're just paying attention to understand what's going to happen, with a single little neuron. Yeah. Okay. So I mean, we discussed this. Each node or perceptron or neuron is internally computing a linear operation, but the output of the perceptron is transformed into a nonlinear output, which is then fed into the next perceptron. That's what we see here. Okay. In our simple example, it was not being fed to another perceptron, it was just being put out. But if you have a deep network like this, obviously it's being fed to the next neuron, right? And this is like a complicated one. This is an example that I usually use, like in my class, for my students to learn. And the idea is that when you want to make a steak for your friend, there are different parameters that you incorporate into preparing the steak. And by fine tuning those steps, for example, your friend is sitting there, you are trying to grill this steak at different heats, different salt, different brand of the steak, of the supermarket that you bought it, how much you cook it on one side, what's the temperature of the oven. These are all inputs. Yeah, these are all the X's. Yeah, these are all these yellow ones for the preparation of the steak. Yeah, so you put all of these in there and you vary them. And your friend says, okay, I like the steak, or I give it 10 out of 10, or I give it 5 out of 10. And you go forward and backward. You keep doing this, adjusting the salt, adjusting the heat, adjusting the oven temperature until you finally get the right weights. Yeah, get the right weights. How much salt? How much heat? That is defined by these weights, yeah, that are between the inputs and the single neuron. Okay, so technically, when you are fine-tuning preparing a steak for your girlfriend or your friend or your boyfriend or I don't know, husband or wife or whoever, you are technically adjusting these weights through experience by going backward, forward, preparing it until you get satisfaction. Like, wow, this is matching. And that's exactly what happens in these neurons, yeah? So that's what exactly that process is what happens, when these neurons try to operate. So if I go back to this, so if we were going through this process, yeah, so that's exactly what's going on. You have certain inputs, you're feeding it into this neuron, and you want a certain output, okay? In the case of a deep learning model, the output is known, like when satisfied, like 10 out of 10 state. It's a matter of adjusting these W's that you end up basically having a relationship where you can every time now go and sort of predict how to cook a steak for, I don't know, certain people or certain person or group or whatever. Okay? Of course, analogies fall sometimes, but this was sort of the idea. Anyway, having said that, let me keep this here. And then I'm going to now expand on this. So I have prepared a little code here, okay, that we're going to just learn everything we just talked about in Python. All right. So let me make this perhaps a bit larger. So we are going to import TensorFlow, okay? So you can use a Torch or you can use TensorFlow, but obviously I'm more comfortable myself with TensorFlow. In fact, I'm not very good with Torch. So I'm using TensorFlow and you guys can basically follow it. So we're going to import TensorFlow, which is used, to construct deep neural network structures and for deep learning, right? So we import the TensorFlow library, okay? Once we import the TensorFlow library, we are going to make two vectors, okay? So this is our x vector, okay? These are our x's, 1, 2, 3, 4. Super simple. So TensorFlow.constant, and then we give this vector structure. So very similar to NumPy that we have covered before, but this is a TensorFlow type data, okay? So I'm given a set of x's and I'm having a vector of y's, okay? Now we want to see if the model can go and find the relationship between x and y. In other words, we know the y's, we know the x's. We want to see how do we calculate y from x. Obviously, this being a super simple example and me trying to basically get you guys understanding the concept, anyone look at this would be like, oh, Ali, it's y equals 2x. In other words, a equals 2. Or let's talk now with deep learning, sort of lingo. The weight, yeah? So the weight is going to be 2. So can we see if this model can go and find that number 2? That's our objective, all right? So, okay, so we're gonna assume, we're gonna pretend that this is really difficult. Yeah, these numbers are really hard. We are not gonna look at them and straight away realize that it's going to be 2 times x. We are just assuming. And we want, write a protocol in Python that can go and, basically calculate this for us. Okay? Okay, so let's go and take a look. First, we need to guess, okay? Or we need to start from somewhere. Imagine we are going to be doing this on a sheet of paper. So what would you do? The first thing you do is that, okay, I want to find the relationship between y and x. I'm going to start putting numbers here. You're going to start this game by choosing some value for this weight. And you start with 0. So you say, okay, y equals 0 times x. So 1 times 0, 2 times 0, 3 times 0, 4 times 0, obviously going to give you 0. So definitely that was wrong. Okay? That's not a correct path. You're going to do what next? Well, you're going to increase maybe the weight. Yeah? You're going to say, okay, I'm going to use 0.05. No, I'm going to use 20. I might even use 50. Something random. Yeah? So you choose another value for this weight instead of 0, and you run the thing. Okay, you're going to get certain y values. Let's say if you choose 6, you're going to say 6 times 1, then you're going to get 12, you're going to get 18, and then you're going to get, sorry, did I say 6? Yeah, 24 basically, yeah, 18, 24. Well, you take a look and you're like, no, that didn't work out. I need to repeat again. But hold on in that moment. So if you chose, let me say, if you chose 6, okay, if you chose 6, you are going to get what? You're going to get multiply them by x, you're going to get 6, you're going to get 12, you're going to get 18, and you're going to get 24, okay? And you're going to compare this, you're going to compare these with these. Well, how close are you? Was it good? Was it bad? Well, how do you assess that? How do you decide that how bad this was, how good this was? You need to have a parameter, or you need to have a definition of an error, okay? So you need to say that, okay, choosing 6, so you need to be able to say, 6 caused how much error, and if you chose 5, is this error higher or lower? That is very important, guys. Yeah, that is super important. I mean, in fact, that is the foundation of deep learning. Yeah, in terms of how you go by adjusting these weights, super important. So far we realize that we have created this dummy data. We want to find this weight. In fact, we want to calculate the weight, but we set up the weight to be as 0. All right, we pretending that we are writing this on a piece of paper. And every time we put a value, we're going to calculate and we're going to find out how much error is there. Okay? First of all, if I was to say that, okay, 6 is not good, let me go and choose 5. Okay? What's the difference between 6 and 5? It's just 1 digit. Why not 7? Why not suddenly hop to 10? Why not hop to 1,000? Yeah? So, would you agree that if we were doing this and you see a huge error, yeah? So instead of, I mean, imagine if I chose, instead of 6, I chose 1,000. All right? So what am I going to get here? I'm going to get 1,000 here. I'm going to get 2,000 here. And I'm going to get 4,000 here. And now the error between what we got, choosing, if we choose 1,000, yeah? Now the error is huge, isn't it? Comparing this with this. So if I was to change 1,000 now, okay, would I come and say, oh, okay, 1,000 didn't work, let me try 5. Sorry, let me try 999. Would I do that? Well, I'm still going to have a ginormous error, isn't it? So if I have a ginormous, huge error, I can adjust and change, yeah, this weight that I'm guessing at a larger scale. So, for example, from 1,000, I can drop suddenly to choosing 500, yeah? I can go and say, okay, let me quickly half it, yeah? Big drop. But if when I was at 6, yeah, when I was doing 6, did it make sense that if I from 6 go to 5.5 to see if it makes an improvement? Yes. So depending on the error I get every time I choose a weight, choose a number, okay, depending on the error I get, I can, you know, come up with a new idea with a big gap between the original weight value or the second guess I'm going to have, or the second decision I'm going to have. And that is fundamental to this idea. Okay? So let's see, what do we do here? So let's look at the Python logic. So we are going to say weight equals, we're going to initialize. So technically we are initializing weight as 0. We're going to start with 0. Learning rate. That learning rate relates to what I was talking to you about. Yeah? If I get an error, if I get a massive error, like when it was like 1,000, how much I'm going to adjust, okay? You know, like for example, moving from 1000 going to 999, or no, dropping down, you know, by like 500, 300 or so. That learning rate defines how fast, sorry, how extreme I'm going to be changing the weights that I'm basically calculating to see ultimately what weight gives me a good Y. Okay. So that's going to be my learning rate, how fast I want to change the numbers. And then I'm going to write a for loop. Okay. So you're all familiar with for loops. Okay. And I'm going to call that epoch. So usually we say for I in range 10, print Ali is great. Yeah. And then it will print Ali is great, Ali is great, Ali is great. All right. That's a for loop, typical for loop. I'm not going to call it I. I'm going to say for epoch in range 100. So for 100 times, now this is new. Okay. With TensorFlow, dot gradient tape as tape. Okay. I'm not going to, I will refer to this maybe later if you find, but just take my word for it at the moment. So with this instrument, so we are calling a method, from TensorFlow, which is referred to as gradient tape. It's a function. And we're going to just shortcut it as tape with TensorFlow.gradient tape as tape. So this tape is now going to represent this function of TensorFlow. Predictions equals weight times x. Okay, weight, which is going to be 0 first. When we start this right at the beginning, weight is going to be 0 times x. X is what? This vector. That's exactly what we would do on a piece of paper, isn't it, guys? If we were to, you know, practice this, you know, trying to find y. Let me get rid of this, by the way. That's going to give us another, right? So we first make the first predictions, just as we did before, and we're going to get what? 0, 0, 0, 0, 0, because everything is going to be multiplied by 0. All right, fine. So we make a set of predictions. All of them are going to be 0. And then compute the loss, mean squared error. So loss equals TensorFlow dot reduce mean. It means find the mean. Yeah. You know NP dot mean with NumPy. When we did NP dot mean, just let me write it. NP dot mean. Okay. With TensorFlow, you need to say reduce mean, and I don't know why they use this term. I mean, why couldn't they just say TensorFlow dot mean? But reduce means just NP dot mean. You know, find the mean. TensorFlow dot square predictions. What's predictions? Exactly what we just predicted with the 0, 0, 0. So 0 minus all of that. Okay. So I hope that you know what mean squared error basically is. Yeah. So technically, when I told you that we try to find out how much mistake we had with our calculation and what the outcome should be, we use mean squared error as that. Yeah, so we are using mean squared error to see how bad did we do. That's all we are doing. Okay, so far, not rocket science, right? Okay, we measured this loss as well. Okay, how bad did this happen? Okay, and then look, I've put this function here. If epoch divided by 10 equals 0, meaning at every 10 epochs. Okay, so this has nothing to do with deep learning at this stage. I'm just trying to have the program report to us. So every 10 steps after every 10 epochs, other words, every 10 times that we have chosen or calculated a new weight, I want this thing to come and print which epoch we are at, what was the loss, and what was the weight. You know, initially we start with weight 0, okay? And weight.numpy, because why am I saying loss.numpy, weight.numpy? Because the weight and loss here are calculated under TensorFlow. So using .numpy converts them back to NumPy array so we can see them, yeah, NumPy numbers. Anyway, you can then go and take a look at this with ChatGPT and ask for help, yeah? But provided that you understand the idea in this lecture, you understand what's going on, then you can, if you have like confusions about why I'm using loss.numpy and not just loss, as I said, I'm converting a TensorFlow type data into NumPy. That's what it is. But for this sort of understanding, you can go and use ChatGPT or other sources. Anyway, so that just reports to me what's going on. But then this is important. This is now again going to the heart of, deep learning or what we think is deep learning. Gradient equals tape. Remember this tape guy? Tape dot gradient, dot gradient loss and weight. Okay? So it says compute the gradient of loss with respect to weight. Okay? And then print gradient. Now, gradient is like a derivative, yeah? So rate of change, guys, yeah? I hope you have covered this in calculus. So y equals x2. dy over dx is, 2x, basically. That's the derivative of it. But then when it becomes more complicated, I will show that to you in a bit, yeah? So you will then have chain rule, and really I can't cover those. These are like calculus concepts. But gradient is basically rate of change. So it's the rate of change of what? I want you to pay attention to that. I'm trying to to find the gradient, the derivative of loss with respect to weight. How is the weight I'm choosing is affecting the speed by which this loss is changing. You remember when I said here, if I chose first number, I chose 1000, yeah? Then I'm going to have 1000, 2000, 3000, 4000. That's going to be a huge error, isn't it? Comparing it to 2, 4, 6, and 8. So how would changing that weight, okay, change the speed of my error? In other words, my predictions becoming closer to the real data, how fast they are getting there. Okay, and that is fundamental to calculating this. So gradient, we measure the rate of change, okay, of loss with respect to the weights that are being calculated. But then here, obviously, we have set the weight equal to 0, isn't it, so far? Okay, so if the weight is equivalent to 0, what? This loop is going to go forever doing the same thing, isn't it? So we need to update this weight. We need to choose a new weight. How do we choose that? Weight that assign sub. This function, assign sub, means, okay, weight that assign sub learning rate times gradient. Okay, this means new weight, adjusted weight, substitute the weight. Assign sub does that for you. So it means get the old weight. In this case, the initial one was 0 minus learning rate, which was what? 0.001 times gradient. Okay, times this gradient. What you will notice, and I want you to sort of think tonight, sit down and think about this, yeah? What this sort of does is that, okay, it basically adjusts the weight based on the learning rate that you give and the gradient. Okay, so the larger the gradient, meaning the rate of change being bigger, okay, it's going to cause bigger change to the weight. As the gradient becomes smaller, meaning the error is getting less and less, then this value that is subtracted from the previous weight, yeah, previous, by old weight, it means one step before, is going to be a smaller. All right, so let's go and now run this. So I'm going to try to get this model to learn really slow. Okay, and this is super simple. We want to see if this algorithm, we are trying to imitate a single neuron, but without a kernel function, without an activation function. So this is still a linear one, yeah? I haven't added activation, this thing. I haven't added a function here, yeah? So we are just doing pure multiplication, okay? So that you get the idea. So, and then what else do we have? Nothing. Print weights.numpy. So let's run this, guys, and I'm going to actually reduce the size first so you can see it. So that's the entire algorithm. We walked through it. Let's see what do we get. I've run this before, so I'm hoping that I'm not getting an error or anything. Okay. Well, Trained weight 0.02. Yeah. So did this learn anything, guys? I mean, look at that. It did the entire 100 steps. It started with loss was 30. Why is loss 30? Mean squared error. You can calculate it by hand, guys. Yeah. So if you're going to be calculating it is, like all of these being 0 and these being the number, the mean squared error between these two vectors, you basically are going to get 30. And initial weight, we set it to be 0. And then look at that. What is this, guys? What am I printing here? Print gradient.numpy. That's the gradient of it. So at the moment, it's like as if I'm telling this model to go and learn this, but it's learning it really slowly, isn't it? Okay? Because it's trying to adjust the weight at a step at a time. So how about if I go and increase the learning rate? So I'm going to make it like this. Let's see. So ideally what we want this thing to come and say the trained weight equals 2. But look at that, it's 0.27. So he hasn't really learned anything, has he? Well, is it because our model structure is bad, or is it because we are basically trying to make our model too clumsy, forcing it to learn too slowly, given the problem? Because it's a very simple problem. And we are forcing it to sort of act like an imbecile, basically, like learning at such a slow pace. So I just increase that. Let's see if we can get it to find 2. So this time, significantly improved, yeah? I told my model to learn faster, okay? And it went and managed to find number 1.55. So it's guessing that the relationship should be 1.55. I can do 2 more things, guys. I can do 2 more things. One is that I can come and tell it to learn faster, or I can tell it to practice longer. So what if I make this 200? So I'm telling it to go and repeat and practice more, try more numbers. That's what I'm saying, yeah? At the same speed. Let's see what do we get. Now that I give it more time, look, it's reaching 1.84, 1.86, 1.88, 1.9. So it's learning now, yeah? Possibly, what if I told it, go to 300 epochs? So now it's practicing 300 times. Well, it's going to 1.97, okay? Which is fair enough, like considering that it's trying to guess number 2. So more or less, it's almost getting it right, okay? Now, alternatively, what if I went and I returned back to 100? Okay, let me put this here, and I'm going to shorten the learning process. Okay, so I'm making the learning rate faster, okay, which is going to be affecting this part of equation, so the weight assigned part, yeah? Let's see what do we get. 1.99996, all right? Now, believe it or not, later on, when you develop really sophisticated deep neural network models, you will realize that sometimes altering something like number of epochs and learning rate makes such a big difference. You see, before I was having a slower learning rate. It was a slower, okay? So in other words, it was like as if I was telling my kid to learn slower. Don't rush it, don't get panicky about, preparing for exam or whatever. Learn slower. And I was telling it to even practice more, and it was underperforming. And now that I've told it to go faster, learn faster, and you have less time or less repetitions to train, it actually went and did better. Well, this is not always the case. The fact is, the message I want you to take away is that with deep learning models, these are, later on, you will realize that they are called hyperparameters, for example, in your model. So learning rate, number of epochs can play such a critical role into finding an accurate, basically finding. But what I want you to also take a look here is this idea. Guys, these are the gradients that I'm printing here. Okay? These are the gradients that I'm printing here. Just please take a look at each epoch. So this is epoch 0. We got the loss, huge loss. Weight initialized at 0. Okay? We just 0. As if we could have randomly selected it as well, but we just set it at 0. So we have a huge loss. We have a huge gradient, basically. And but what's happening with this gradient after every epoch? Look, through the first 10 epochs, it's going down. 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 Look at the value of the gradient. Do you realize at every step, I mean, look at this, going to -5. The gradient, yeah, is becoming smaller, smaller, and smaller. Okay, so let me just go. So the gradient is becoming smaller and smaller and smaller. What does this tell you? Well, when you read about the idea of deep learning, the pillars of deep learning is all about the, sorry, I brought the wrong slide. It's all about this, yeah, gradient descent. So you got an error function, loss, okay, with regards to weights. We are calculating the loss, with respect to weight. And your hotspot where your error is going to be minimum and you are going to be predicting the correct weight that can predict y for you is when you find its hotspot, when your derivative or your gradient is at its minimum. And take a look at here. What is this process is doing? How is this model, this AI model, so a super simple AI model, let's call it. It's like super simple AI model. How is this learning to go and find that number 2? Look at the gradients, yeah? Starting from -30. So the process of gradient descent is going down and down and down. And look at the weight, okay? Look at the weight. Look at the loss. As that's going down, the loss is decreasing, basically, yeah? And it's so important that you grasp this idea, guys, yeah? That what's happening here. Now, I have written some mathematics here which explains the ideas basically behind this. But as I said, you really need to know the maths before. But just quickly, how weight inside the inside the loss function. So y predicted or y predictions or y hat is y predictions was the weight that we were guessing or initialized multiplied by x1. Okay, xi, vector of x's. So we can write the loss mean squared error. That's what it is, isn't it? So y real or actual real y's, y vector, minus or weight multiplied by, x vector, which is our y predictions. So real y minus predicted y, square it, divided by the number. That's our loss function. Now the concept of chain rules, we are doing a derivative of this function, this loss with respect to the weight. We are doing a derivative of this, yeah? And what do we get? If we consider this whole thing, as A, yeah, applying chain rule. And if you don't know what chain rule is, you need to go and find out, yeah? So if you apply chain rule to find the derivative of loss with respect to weight, okay? So first, we consider this whole thing as A2. We could have, I call it Mickey Mouse to the power of 2, yeah? But anyway. So dA2 divided by dA equals 2A, okay? And then differentiate the inner part. Yeah, the inner part is y minus x, so that is, what is the derivative of this? Okay, forget about y. You're going to have, there is no power to it, so you're going to just get x1. And it's going to be minus because of this. So you're going to get minus x. So ultimately, that multiplied by that, this is going to be your derivative, yeah? Sorry, your gradient rule. Now, consider this. So we found the formula for a gradient, how to calculate gradient. In our example, we had x equals 1, 2, 3, 4. Y was 2, 4, 6, 8, right? And how did we go through predictions? Okay. In this case, I said that we initially started with 0. So our predictions are going to be 0, 0, 0, 0, 0. Okay. How do we measure the error? Y hat is our predictions by choosing weight as 0 multiplied by x vector. Error is y minus y hat. So we are deducting, yeah, or x's, or y's, yeah, y's, minus our prediction. So minus 0, minus 0, minus 0. Calculate the gradient. And what gradient do we get for this? We get minus 30. So once you do this basic math, yeah, we get minus 30. Now, just one step. So do you realize that? Gradient equals minus 30. What do we have here right at the beginning, guys? Okay. Minus 30. Okay. So I thought like I'll show you how this calculation is done as well at every step. I've just shown you the calculation for this. Yeah. I'm just showing you the calculation for this. But in reality, this algorithm did these calculations 100 times. And how did it do it? And it updated the weight. And that's what we're going to see now. So once we calculated the gradient, which was minus 30, update the weight. So new weight equals old weight. Well, old weight was 0. Yeah, because we started with 0. Minus learning rate, which was set at 0.001 times minus 30 equals 0 plus 0.03 equals 0.03. So when the loop starts again, this time, when the loop starts again, this weight is going to be 0.03. Okay? And this process continues until it chooses a weight that finally gives us minimum error. So when it chooses something near to 2, will ultimately make this error what? 2 minus almost 2 is 0. 4 minus almost 4 is 0, because 2 multiplied by them, yeah? 6 minus almost 6, 8 minus almost 8 is going to give you a very, very small error. And thank you very much. Your model is trained, basically. That's the idea. You really need to understand this before you say that, okay, I'm going to learn more, complicated deep learning protocols. If you understand this idea, then everything else becomes easy. It doesn't matter how many neurons you have there. It doesn't matter how complicated your neural network structure is going to be. It's going to be simple. Now, except that, obviously, we don't do it in real life like this. This was complicated because I wanted you to learn what's happening under the bonnet. Most probably, if you go and you try to learn this on internet, if somebody was going to show you this in internet, it's going to be much simpler when they teach you, because they will come and show you something like that. Okay? So this is exactly the same thing, except that we are going to get TensorFlow to do it for us. So you can see the coding is much, much less. It's going to do exactly the same thing. So x equals TensorFlow constant that, y equals TensorFlow that, except that this time, instead of what we did manually, okay, we're going to basically get this thing to get TensorFlow to do it for us. So we're going to say model equals TensorFlow.keras.sequential, okay? We use the sequential class of TensorFlow, okay? And we create a single neuron in there. Look, TensorFlow.keras.layers.dense unit equals 1. It means I want 1 unit. Now this use bias equals false. Forget about the bias for the moment. We are not using a bias. Okay, so I'm just going to set it bias. So I want this to be exactly the same as what we did before, so you can make connection. So all we did, instead of manually creating a neuron operation, we are using TensorFlow cross.sequential. Okay, done. That's the name of our model. Once we have done that, then we're going to say model.compile optimizer TensorFlow.keras.optimizers.stochastic gradient descent. And look at that. We are defining a learning rate there. Okay. And then loss equals MSE. So literally before we manually chose we formulated in Python how to calculate the loss. We did it manually. We set the learning rate separately ourselves. And how do we adjust the weight? We just used a very simple operation. Deduct the old weight from, like learning rate multiplied by, I don't know, the new sort of weight and all that. Yeah. This time we are using a predefined method like a stochastic gradient descent. Or you can use Adam optimizer. That's a different model. I hope you go and learn about this. Or if you have familiarity, I hope it makes it clear to you what's happening. Yeah. Then once that's done, model.fit epochs equals 100. Again, we did everything manually before, so I want you to later on look at the previous code, which was manual, and this one, which is automated via TensorFlow's sequential class, yeah, and see what's the difference is. Now you might be like, oh Ali, if we could basically write a code like this, why do we need to bother basically using sequential? Well, believe me, this is only for a single neuron. Whereas with the sequential model, you can literally make huge neural networks. Can you imagine how much code writing you need to do? Whereas with the sequential class, all you need to do, you basically come and just define the number of neurons that you want to have in there. Okay? So, just one neuron. Let us see basically what do we get out of that. All right, so more or less, it literally went trained weight 2. Okay, so how did this work? Let me just go back up. Did I go for what epoch did I have? Yeah, 100 epochs. Variables equals 1. So I went through the 100 epochs, print, except one thing, guys, model.trainable variable. So before we defined weights, we were asking it to print weights and all that because we did everything ourselves. Here, you need to use callables and functions from your model, which is an instance of the TensorFlow sequential class. Okay, so I'm basically saying that once you have fitted it, tell me what is it. In fact, I think we don't even need to go to 100 epochs. Maybe, I don't know, let's see, 30 epochs should do it probably. Find number 2 for us. Yeah, okay. Because, I mean, look at that. The loss is becoming almost 0. You see, this is technically outperforming my manual model. Why? Well, because sequential in TensorFlow, developed by Google, is obviously an super optimized operation, like for deep learning. All right. But that's the basic structure of a deep learning model. I will try to upload an old video on how you will actually use this for regression or classification analysis, but then that's not going to be part of your course. You can just watch that on your own time. So I hope, guys, you have enjoyed it. This was an introduction to the foundations of basically, deep learning, the concept.